Hello, and welcome back to class number 2 of our Physics 120 pendulum experiment. So, in the last class, right, let me just start by recapping what we did. We used Newton's laws to derive a differential equation of the motion for the angle theta made by the pendulum bob from the vertical as a function of time. Right? So we wrote down this differential equation, where we want to solve this to find theta as a function of time. And my pendulum bob just rolled off the table. Never mind that. Stay. So after we applied Newton's laws, right, as I mentioned, we can't solve this differential equation exactly. So we applied the small angle approximation, namely sine theta is approximately equal to theta for theta much less than 1 in radians. To simplify this to d squared theta dt squared equals minus g over L theta equals 0. And then we showed that something that goes like cosine omega t is a solution to this simplified equation if my omega, my angular frequency, is root g over L, and that's how we concluded that the period is equal to 2 pi the square root of L over g for small angles, and that's because, right, only for small angles is this simplified differential equation valid. But you might ask the question, well, we worked out this theory for small release angles, and that's what I tried to do in procedure part A. But what if I want to think about what happens when I let a pendulum go from a larger release angle? That's the question we're going to answer today. In particular, we're going to go and use energy methods to calculate the period for all initial angles, and this, I'm going to get a cup for this so it doesn't keep rolling away. Okay, so let's just examine this physical system once again, right? So again, what we're assuming is that we release the pendulum bob from rest at some initial angle theta naught, and we let it go, right? Notice that the pendulum reaches a turning point, right, where it's momentarily at rest at either extreme of its motion. Right? So that's a fact we're going to harness when we do an energy analysis. So many of you had me for Physics 117, and you'll probably remember that when we think about applying energy, there's a few things we always want to do. We always want to clearly define our system. We also want to clearly define our initial and final states. So let's just start with our system. Okay. So I'm going to define. I have several possible choices, but for convenience, I'm going to choose my pendulum bob. And the Earth to be part of the system. So we do need to think carefully about this, right? Because, right, if I'm defining the system this way, right, the string here is outside the system. However, right, if we think about what's going on carefully, right, the tension force exerted by my string is always going to be perpendicular to the motion of my pendulum, which is moving in a circular arc. Right? So if my string is outside the system, there's still no transfer of energy, there's no work that's done by the string on the system. So we still have an isolated system defining it this way. Okay, so let's think about a couple of points where we can try to analyze what's going on. Right? So let me just draw a couple of pictures. So let me first draw the case when we release the pendulum bob at theta naught. Right? And if we release it at this angle here, right, it's going to be momentarily at rest here. So there's going to be no kinetic energy in the system. Okay? Let me draw sort of an intermediate point here. So where the bob has started swinging, and now it's at some smaller angle, which I'll just label theta. And then let me also draw another instant when the bob is hanging straight down, so theta equals 0, and it doesn't matter which way the bob is moving, but we assume that, let's assume for sake of argument, the bob is moving to the left. So to apply the energy law, we're going to want to think about what kinds of energy the system is going to have here, right? So here we know if we're releasing the bob from rest here, at this point, and if I'm at rest, I have no kinetic energy, so K equals 0, right? But K is definitely non-zero at either of these 2 points, since my bob is actually moving there, right? So we drew a little velocity arrow there. The other kind of energy we can want to think about is the fact that there's an interaction, there's a gravitational interaction between the pendulum bob and the Earth. They're both in the system, so that means that there's a gravitational potential energy associated with the interaction between these 2 things in my system. So I want to think of about my gravitational potential energy. As we talked about in 117, gravitational potential energy just depends on height above some 0, which can be arbitrary. I didn't do the greatest job of drawing this here, but I'm going to consider y equals 0 to be the height when the bob is hanging straight down. So I'll take here, so the bob is hanging straight down, I'll take that position to be the 0 of my gravitational potential energy. You know that gravitational potential energy goes like mg delta y. So for any other point in the swing, so like if I release it here, the pendulum bob is higher, there's some gravitational potential energy in the system there. There's also some, but less, gravitational potential energy when the pendulum has swung down to a smaller angle. So not to belabor things too much, but just to draw a picture of what's going on, I want to go and draw an energy bar chart, the way you probably did if you took 117 with me, and I'm pretty sure you did if you happen to have taken it with, say, Matt Price or Kelly Sullivan. So let's go ahead and do that. So we just sort of schematically show in a cartoon fashion the energies that are present in the system, right? So so we've got kinetic energy and gravitational potential energy, and so at this point when we've got the pendulum bob at its maximum angle, let's say we're releasing it from rest there, we know we have no kinetic energy, but we have some amount of gravitational potential energy. So I'll just arbitrarily draw 3 units worth. Now, what I forgot to mention is that we've got an isolated system here. So according to the energy principle, what does that mean? Right? Remember that the energy principle for an isolated system says that the change in energy of a system is equal to 0, right? Because the right-hand side is where work or any other transfers of energy would appear if we had them. But we have none. So delta E of the system is always 0. So in other words, E sys is constant. And we can see that in our bar graphs. So maybe the easiest case to draw is sort of this other extreme here, where we now know that if I set the height here to define the 0 of gravitational potential energy, at this instant, my UG is 0. Well, by the energy law, that has got to be, all of the system's energy has to be kinetic energy, and I can draw the bar chart like this. And it shouldn't be too hard to convince yourself that in this middle situation, we're going to be somewhere in between. So here, again, I'm not going to worry about the details, but we'll just sort of draw this in a cartoon fashion. Let's say there's 2 units of kinetic energy and 1 unit of gravitational potential energy. So, I think now we've gotten a good conceptual picture of what's going on. Here's what we're going to do. We want ultimately to work out an equation for the motion of the pendulum at any angle. So we're going to want to consider this particular case. We also want to think about, right, what happens when we do know that we release the pendulum from some initial angle. So it kind of seems important to capture that theta naught in there. And so what actually we will do is to look carefully at applying energy of the system as constant to these 2 points that I drew here. So I'll call this initial. I'll call this final. We'll do it for an arbitrary theta. If we do our math right, we should be able to sort of capture the theta equals 0 result in there as well. Okay. So just to give you a little bit of a preview of what we're going to do. So here's what we'll do going forward. Going to apply. Oops, this marker is going. These markers really go fast. I'm going to have to go and buy some more at some point, but who knows how long it's going to be possible for me to get more markers. Energy principle. What we're going to end up doing when we apply the energy principle, right? There's going to be a kinetic energy term in here. The kinetic energy, maybe it's plausible that it depends on d theta dt, the angular velocity of our pendulum bob, and so we'll get a differential equation for d theta d t, and then what we'll end up doing is we'll essentially play some math tricks to calculate the period, to get the period. Again, the kinds of tricks we're going to talk about today, I would not expect you to come up with on your own, but it's good to see how this can be done once in one's life. Okay, so let's analyze this carefully. So we said here that at this initial situation, when my pendulum bob is at theta naught, so either when I release it, or if I've swung all the way to the end, V equals 0, so there's no kinetic energy, and I only have to worry about the gravitational potential energy, right? So E sys equals kinetic plus gravitational potential energy, and this vanishes, right? And my gravitational potential energy is going to be equal to my mg delta y, above, so my height above my 0. So we can go and calculate that carefully, right? So let's draw in a few lengths, right? So we know, right? We know that this entire thing, that's the length of my string, right? The height we care about is this height here, delta y. So that's how high the bob is above this point here. If you look at this diagram, right, you can see that, right, that delta y plus this piece here adds up to L. Let me draw that in a different color. So that's pretty bright, so let me, right, this green piece over here, well, that we can find out using some trigonometry. Notice that we've got a right triangle here, right? That's my hypotenuse, which also has a length of L. I claim, I think you can convince yourself, that this green piece here has a length of L cosine theta, right? And it's cosine because, right, we want cosine is adjacent over hypotenuse, and this green leg is adjacent to my angle theta naught here. So I claim then that my delta y is equal to, so it's going to be this entire thing minus the green piece, so that's L minus L cosine theta naught, or I can factor out the L, which gives me L1 minus cosine theta naught. Okay, well, let's just double check that. Right, we can check that by thinking about limiting cases, which is something I always recommend. So we work this out for an arbitrary release angle, an arbitrary theta naught. We can think about what happens if I release it from theta naught equals 0, so if I don't do anything to it. If, right, my theta naught is 0, then I've never actually picked up the pendulum, I've never given the system any any delta y, right? If theta 0 is 0, cosine of 0 is 1, so delta y equals 0, which is in fact plausible. So that's always a good check that we didn't make a silly trig mistake. So right here we can right away conclude that the E sys initial is equal to L mgl one minus cosine theta naught. Okay, so let's think about now the energy of the system in this final state. Now we have final equal, we have both kinetic and gravitational potential energies to worry about, and they're both non-zero. Now the gravitational energy piece, we can basically do what we did over here, right? This argument holds for any valid value of theta. There's nothing particularly special about theta naught that we invoked here, right? It's still going to be geometry. It's going to be some different delta y. So if we just copy over the result, right? UG final. Okay, I'll be good and label these both as final. UG final is going to just be this with theta instead of theta naught. That's going to be MGL 1 minus cosine of theta. So the last bit is just to get the kinetic energy, right? So K final, 1/2 m v squared, where v is our speed. Let me draw a little velocity arrow here. Now, what we need to remember is, right, that this pendulum bob, right, this pendulum bob is undergoing circular motion, right? And so we can relate its linear speed v to the angular speed d omega or d theta dt of the bob. So relate, and we already had to do this when we applied Newton's laws last time. So relate angular and linear speeds. Right. And what we find is that v equals L, so which is the radius of the circular arc, right, times my angular speed, omega, or d theta dt. So my final kinetic energy is equal to 1/2 times m times v squared, which is L squared d theta dt, the quantity squared. And now we can just combine these two things to get E system final, right, equals 1/2 ml squared d theta dt, quantity squared. Oh, when I'm running out of board, let me just scoot. I'll rewrite that scooched over. Okay, so that's E cis final equals 1/2 m L squared d theta dt, quantity squared, plus mgl 1 minus cosine. Now, according to our energy principle, right, these two things, E system initial and E system final, ought to be equal to each other. So in the next scene, what I'm going to do is I'll erase the board and then I'll just set these two equations equal to each other, and we'll be able to indeed get something that involves d theta dt. All right. Our goal now, so I've copied over from the last scene, our goal now is to solve for d theta dt. So at this point, we're just going to have to massage this algebraically. We are helped by some things. It helps to sort of be strategic and look before we dive into algebra. So a few things. Notice how there's a factor of m in every single one of these terms. Well, that means that we can just go and cancel out those m's. We can divide both sides of the equation by m. And then, so I'll just slash the m's out because we're going to be able to cancel them. One other thing to notice, right? Notice that there's if I multiply this out, I get a GL from this times this. But I also get exactly the same thing on the right-hand side. I have GL times 1 over here as well. So I have two of the same term on both sides of the equation, so I can subtract GL from both sides and not worry about that. So I'm just going to cross that out as well, since we know that those two terms cancel. So that already helps us a lot, because we can now simplify a whole bunch of this. Right? So this now becomes minus GL cosine theta naught. Here on the right, we already canceled an m, so this is now 1/2 L squared d theta dt, the quantity squared. And then similarly over here, we have a minus GL cosine of theta. Okay. So this is already looking better, right? We can now, what I'm going to do is I'm going to add this term to both sides. So I'm just going to move this over to here. So I get a GL cosine theta minus GL cosine theta naught equals 1/2 L squared d theta dt quantity squared. Look, these are almost the same, right? I can there's a common factor of GL in both of these terms. I'll go and factor that out. Right? So I get a GL quantity cosine theta minus cosine theta naught equals 1/2 L squared d theta dt quantity squared. Well, to get d theta dt squared, at least, I just now have to shove these two factors here over to this side. I do that by multiplying by 2 and dividing by L squared on both sides. So I get a 2 and a G. Dividing by L squared, L over L squared means I have an L downstairs. So I am left with 2G over L cos theta minus cos theta naught equals d theta dt quantity squared. So we're getting better. It's not yet maybe clear how we can go and solve this, but we're at least driving towards a differential equation for d theta dt. Well, what I'm going to do is now take the square root of both sides of this. So take square root if I take the square root of both sides, and I'm just going to rearrange this, I'll just flip the order of the two, flip the sides around. So I'm going to end up with d theta. Okay, and I'm going to take either the positive or negative square root. I'm just going to remember that that's possible. I'm going to write this as plus or minus square root of 2g over L cos theta minus cos theta naught. Okay, so we have now arrived at a differential equation for d theta dt. The next step is, what do we do about solving it?